This phone is so big to fit in my pocket. I wish I could have it in my eyes. Not possible. But why? I will tell you why. It cannot fit in your eye. What is the reason the sun is able to achieve fusion even though there is not enough temperature in the core? How is DNA capable of spontaneous mutations? The answer to all of that is one thing. In our classical world, a ball cannot go up a ramp if it doesn't have enough kinetic energy to match the potential energy. But in the quantum world, a particle can just pop up on the other side even if it doesn't have enough kinetic energy. The wall here is called the potential barrier, which represents the energy needed to overcome repulsion. In 1927, Friedrich observed this strange phenomenon and named it quantum tunneling. Yeah, you heard that right. This belongs to quantum mechanics. Don't worry, it's not rocket science though. It's more than that. The problem arises when we consider the particle as a point, but in the quantum world, nothing is certain. This occurs due to the Heisenberg uncertainty principle. The quantum world is probabilistic. So in the quantum world, a particle is not like this, rather this, like a wave. So now, we cannot say that the particle is here or here. Rather, it is represented by a wave. You said a particle is like a ball. Now, it waves too. The wave is not the particle itself. Rather, it represents the probability of finding it. There are the peaks where it is more likely to be than the troughs where it is less likely to be. So, what do these waves do now? So this is how it works. I will explain it to you. When we get to waves, we remember light and Maxwell's equations. And they say an interesting thing. When light hits a boundary at its critical angle, it completely bounces back. This is called total internal reflection. But we have to notice this tiny tail coming out. This is called an evanescent wave. Alright, stop. So you say that total internal reflection is not total? Well, you're right. But since it decays exponentially, we cannot notice it in our daily lives. But at the size of these particles, this is still significant. Similarly, a particle comes and hits the barrier, producing an evanescent wave. And if the barrier is thin enough, the wave actually propagates. So there is a non-zero probability of finding a particle here too. Yes, the particle has crossed the wall. This is what happens in smaller gadgets too. The small size of the transistor gates will let electrons tunnel through them even when the gate is closed. Alright, I get it. But for now, I'll just carry it. Okay.